We're going to start our lesson off with going back over some basic conversions for exponential and logarithms. So remember when we're converting, log the base b, whatever number could be there, to the a means what power must the base be raised to result in a. So for example, log base b to a equals x. We can do the round the world method and think b raised to the x gives us a. So the first form here is in log form, and then when we convert it, we're converting it to exponential. Now the log form takes the results and it gives you the exponents. So that's what you're solving for. And then the exponential form takes the exponent and gives the results. So remember, they are inverse of each other. So let's do a couple simple ones to evaluate. So we have log base 2 to 16 equals what? So we could put an x here if we wanted to solve. We're thinking about really just rewriting this. So when you think about, you take your base is 2, raised to what, we can use an x there, equals 16. So we have to think 2 raised to what gives us 16. So this is where knowing your exponents come into play. So you should be able to tell pretty easily that 2 raised to the 4th is 16. So then that x is going to be 4. Now with the second example, our base is 5. So our base, 5, raised to something, we don't know, we can call that x, equals 1/25. Now here's what we have to know about our negative exponents, because when we have something like 5 raised to a negative, let's say 3, that's the same thing as saying 1/5 raised to the positive 3. So we don't want to have negative exponents up there. They're not happy. So that's the inverse of what they are. So we think about, we know because we're getting a fraction, we're going to have a negative value in our exponent. So the way we can set this up, or way we can think about this, is if we want 25 to be on the bottom, how do we get 25 by multiplying? Well, we know it's 5 squared. So this is the same thing here as 5 squared. So we can think about this as 5 to the x equals 1/5 squared. That would still get us 25. Well, if we want it to match and be as the base, because it's not right now, it's 1/5, and then that 5 raised to 2, we have to think about flipping it. So we can think about 5x is equal, and if we do the inverse, we have 5 to the 2. Our bases are the same, so they kind of cancel each other out, or are worth the same value, so then we know that the exponent has to be 2 for that one. Now remember, if you do not see a base in a log form, that's called a common log, and it is 10. So for example, log of 100 is the same as saying log base 10 of 100. And we could solve that the same way. We put our base here, raised to what as our x, equals 100. And then we can think about how could we solve 10 times to what value equals 100. Again, knowing your exponents there. Now, let's look at a more complex looking one with a radical sign. And we can think about these a little bit as the same exact way, but we got to think about them in a little bit different form. So I wrote this form for you, log, and we're using a common log 10 of the square root with a little index here of n. So when we look right here, this is our index, and then x is underneath with raised to the m power. Now that m could be a 1, it could be nothing there, so it's a 1. This converts to the x being raised to the m, what it's with, divided by the n. So for example, this one here is log of the 5th root of 1,000. So we're going to change that to show the common log. So we remember this is the same thing as log base 10, and I'll rewrite here. So this is the same exact thing. So now we want to set it up. We take our base here, and we raise it to something, and it's going to equal this. Okay, so we're saying 10 raised to something, you can do an X or a question mark, is going to be equal to the square root, or excuse me, the fifth root of 1,000. Now notice here that 1,000 and 10 are not the same base. So if we're trying to get to the base of 10, we can rewrite 1,000 as the base of 10. So again, knowing your exponent, we know that we can write 1,000 as 10 raised to the third, and put that under our sign, still fifth root. And now we can think about using our form, okay? So we can think our x is our 10, our m is 3, and our n is 5. So 10 to the 3/5, that means our value that we're missing, or what log fifth root of 1,000 is actually 3/5. That's what it's worth, okay, to evaluate it. All right. We talked very briefly about natural logs. We'll go a little bit more in detail in this unit. But natural logs are ln, and a natural log, it means the same thing as log base e raised to the x, and we can actually write it that way if it helps you. But e is a number, and it's about 2.718, so irrational number, just like pi. And so when we're thinking about solving problems like this, so here's a problem, natural log, the base is not seen, so we know its base is the same as log e. So we could rewrite this here as log base e to e to the fifth. And that seems so weird, and it is kind of redundant, but when we have the same base and here, these actually cancel out, and our answer is actually 5. So think about what's happening here. E raised to something is equal to, because we do the round the world, okay, if we didn't know what this was right here, so I'll take that away for a second. If we didn't know what this was, we do around the world, e to something is equal to e to the fifth. Well, e and e are the same, they cancel each other out, so x is 5. That means this value right here is 5. That is the evaluation of it. Now, if we do something even simpler than that, and sometimes they try to trip you up, I want you to remember for this one, anything raised to a 0 power is 1. So let's do a couple examples. So for example, natural log of 7 to the 1 equals what? So we're going to still do it the same way. We can think about it exactly like we did before. This one, like we can think about it as 7 raised to what gives me 1. So 7 raised to what gives me 1? Well, the only thing I can raise it to is going to be 0. So this actually evaluates down to 0. That whole little expression there is worth 0. So when we think about this one with the log base of 3, notice it's a different log besides 7 or whatever, or 10. It can be anything, but if it's got a base and it's to the 1, it's always going to be raised to the 0. So 3 raised to what gives me 1? Well, 3 raised to what gives me 1? The only thing it could be is 0. So this whole expression is worth 0. Now, sometimes they're written very simply like this here. This is a natural log 1. Remember, this is the same thing as saying log of e to the 1. And we know that e raised to something equals 1. Well, if e raised to something equals 1, and we know that the only thing to make it 1 would be 0, this is the same thing as saying e to the 0 equals 1. And if we know that e to the 1 equals e. So know those differences and kind of what they mean. Don't get so wrapped up in that it's a different form. You know these exponent rules. All right, let's look at a radical sign again. Remember that a square root symbol just means half of a power. So let's do an example here. So we've got a natural log, and we can rewrite this a couple ways. If you feel more comfortable writing it as a log to help you see it, by all means do. So log base e, and if we want to think about this radical sign as the same thing as a half power, we can think about writing it as e raised to the half. Okay, so those are the same thing. And if we think about it that way, we can think about it also as the square root of, if we use our rule from before, e to the 1, because there's a 1 right there, and this is a square root, that's where we get the e to the half. Okay, so make sure you understand what square roots mean and kind of how to use that new rule. All right, the next little section we're going to talk about is getting and using like bases. And again, we've done some of these things. So hopefully it's a refresher and then just practicing and you remember. So we have here log base 16 and of 64, and we want to evaluate it. What is it worth? Okay, so when we're trying to find what something's raised to, that's telling us the evaluation of this expression. So if we think about this, 16 raised to what? And I'm going to put a little box there, a little question mark. We don't know what it is. Well, you can put an X. Equals 64. Again, around the world method, 16 to what gives us 64. So notice that these are not like bases. But we can start thinking about, is there a base that they could share that we could rewrite these as? So you think about 1664, both of them we can write as a base of 4. 4 to what power gives me 16? Well, that's 2. So I'm just rewriting the 16 as 4 squared, and so I'm still going to leave my little question mark. I'll turn it to an X up here. And then for 64, I can write it as 4 to the 3rd. Okay, so now I have like bases, and then I have to remember some power rules. So when I have something, an exponent raised to a power, I have to multiply these two pieces. So that is 4 to the 2x equals 4 to the 3rd. And because my bases are the same, I can now cancel those out and just set my exponents equal to each other. And when I do that, now I can solve. So x would be worth 3/2. So if I was evaluating log base 16 to 64, that's worth 3/2. All right, let's try one more. Now this one has a fraction in it, same process. So we start with our around the world, our base raised to something equals what's in the parentheses there. And they don't always use parentheses, but so we have 25 raised to something, we'll call that something x, is equal to 1 over 125. So if we're going to get a fraction here, if 25 raised to something gives us 1 over 125, we know that we're going to get a negative exponent of some sort. So we can rewrite these with like bases. Well, 25 we can rewrite as 5 squared, but it's being all to the x. That 5 to the second is just rewriting the 25. So don't forget the x part. And then here we can rewrite this as 1 and then 5 to the 3rd. That's the same thing as 1 over 125. Now, I want them to be so that I can cancel out bases. And right now, one's in the numerator, one's in the denominator. So in the next step, I need to multiply the powers to powers. So 5 to the 2x. And then here I need to do the inverse. So when he goes up top, he won't be happy, but now they have like bases. So then if they have like bases, these can cancel each other out, and we can set 2x equal to -3 and solve. X equals -3/2. That means log of 25, log base 25 of 1 over 125 is equal to -3/2. All right, let's go into some log form equations. Some of these are very simple solving, and then we're going to talk about just setting up for some more complex ones. So this one is set like an equation, so we actually are solving for this, and so we think about evaluating. And this is going to really help you with the properties when you get more complex and how to do it, because these actually are log base 2 of 32 is a value, and that value is what we're finding. So when we start adding and subtracting and multiplying and all that good stuff together, if we understand what the little pieces mean, then it's an easy way to check ourselves. So we're going to set this up just like we have before. Our base raised to x equals 32. So 2 raised to the x equals 32. So I want you to try to finish that one and then try number 2 and see how you do. All right, with number 1, I hope you realize that you had to change the bases to get 32 to have the like bases 2. Change that 2 to the 5th, and that means that x is 5. So log of base 2 to 32 is worth 5. On the next one, we had log base 5 of x equals 4. So it's just saying 5 raised to the 4 is what? That's a really simple one. So when we look at this one, sometimes we can have a base that we don't know. So this one looks a little bit different. Same process. So x raised to the 5 equals 243. So x raised to the 5th equals 243. Again, this is where knowing your exponents come into play. So hopefully you know that x has to be 3. 3 raised to the 5th, 3 times 3 times 3 times 3 times 3 gives us 243. So we know that x has to be 3. All right, we're going to go up a little level with the next few, and these get to be a little bit more complex. You got to think a little bit more, but still the same premise. So we have log base 8 of x equals negative 1. So when we think about having something negative, we know that if I'm taking my log and I'm raising it here, I'm actually raising it to a negative power to get x. And when I see that, I should realize that that x is actually going to be a fraction. Okay, so then I would think about that as 8 to the negative 1 is the same thing as saying 1 over 8. That will give me x whenever I want to leave it as negative. Now, another example I didn't write on here originally, I think is good to see. It's got a square root in it before we get to the next square root. So let me add this one. So we have a log base x to the 3 equals 1/3. So let's try that one. So we have a base of x raised to the 1/3 equals 3. Okay, so if we ever have a fraction in our exponent, we can try to get rid of that fraction. So we can do that by multiplying that by its reciprocal. So we can think about if we take this whole piece, we can multiply it by 3 because a power raised to a power just multiplies. So that ends up being 3 divided by 3, which is 1. So this equals x. And whatever we do to this side, we have to do to the other side. So then 3 to the 3rd power gives us 27. Okay? And a way to think about that is if we wanted to check back to see if that actually worked, we can think about 27 to the 1/3 is the same as saying a cube root of 27, or what times itself 3 times gives me 27, and we know that we're 3, and that's what we originally had gotten. So it kind of helps you see that a little bit. All right, let's go up another level here. This one is log base 8 of x equals 1/3. So around the world, okay, 8 to the 1/3 is equal to x. Now, we don't want to have to deal with fractions in the exponents if we can help it, so we always want to think about looking at that first. So we're going to go ahead and see what we can do to get rid of that 1/3. So hopefully you see that you can multiply it by 3. Whatever you do on this side, you do on that side. So you end up with 8 to the 1, okay? Obviously, you don't have to write the 1 there if you don't want, and x to the 3rd. And so then it's thinking about what times itself 3 times gets us 8. Or you can think about the cube root of 8. And so if we think the cube root of each side, these cancel out, and the cube root of this, we know that x equals 2. A couple ways to think about that. Also think about 8 to the 3rd, just looking from the get-go like a cube root, and you could have avoided that as well. All right, so let's look at this next one. We have a log base x, and it is raised, it is actually of 1/5, and it equals a negative 1/3, which means it's going to be raised to something negative. So we're going to have a base raised to negative 1/3 and go to 1/5. If you want to try to pause it and stop and see if you can do it, I'll give you a second or so to pause without voice. All right, and now let's see how we did. So we have a base of x raised to the negative 1/3, and then it equals 1/5. Now, these do not look anything close to each other, resemblance base-wise. And again, we have fractions in our exponents, so we want to try to get rid of those. Notice we have that negative, so let's multiply this whole thing this time times a negative 3. That gets rid of that negative. We don't want a negative exponent. So we have x, and this negative of negative is a positive, and then it equals just 1. So that side's done. And we're going to do the same thing to the other, and we have to use a negative 3. Now, anytime we raise a fraction or any number to a negative, we really just mean the inverse. So we can work it out and do 1 to the negative 3, and then 5 to the negative 3, and then flip. But really, all this means is we're going to go ahead and flip it 5/1 raised to the positive 3. Those are inverses of each other. And 5 to the 3rd power is 125. So our x is worth 125. So we think about log base of 125 to the 1/5 would give us a negative 1/3. So you can always go back and check yourself the opposite way to see if you got the true answer. Now our final part, we're going to talk about converting to solve more complex equations. We're not solving these yet. We're going to be talking about that more next week. But we're just talking about setting them up. So using exactly what you learned today to set them up. So again, this time we have log base 6, and then we have this long quadratic there equals 2/3. We're just going to be setting them up. So log base 6, that's going to be our base, raised to the 2/3, I like to use parentheses, equals all of this. Still around the world to set it up. So x squared plus 5x minus 16. Okay? And then from there, we'll learn later how to solve a little bit more extensively. Now, sometimes you have other things in your bases besides just a number or a variable. This one has a coefficient as well, so it's still the whole base. So we're going to do base 2x, and I'm going to use parentheses to keep that together as our base. It is raised to the 2x plus 2. Sometimes you'll see this in parentheses, sometimes not. And then equals 4x plus 8. Okay? So that's how you would set that one up. Now, the last two are a log and a natural log. So if you want to pause and try to see if you can do these on your own and just set them up, not solving, and then check back. All right, for this one, this is a common log. We don't see anything here. So here is where we're looking. If we don't see anything there, we know it's a base 10. 10 raised to the 2 is equal to 3x plus 1. Now the last one's our natural log. And again, if you feel more comfortable, you can convert this over. Remember that natural log, ln, just means the same thing as log base of e. And then everything else would stay the same. If that helps you see it a little bit better, please do so, okay? So in that case, anytime we see ln, we know our base is e, okay? E raised to the 3x plus 3 is equal to 3x plus 8. All right, you have some practice. And hopefully this makes a little bit more sense or brings it back to your forefront, and you'll be ready to go.